Hello, my dear, and I'm glad to see you again. And let's start our lecture on hypersonic dynamics. Okay, today we will be continuing study hypersonic inviscid flow field. And now let's start from the first today's subtopics. Let's call hypersonic small disturbance equation. I hope you remember that the governing Euler equation, which discussed in last lecture, apply to the inviscid flow over a body of arbitrary shape. Large or small, thick or thin, blunt or sharp, no matter. In application involving low drag and, or maybe sometimes, or higher L over D hypersonic configuration. L over D, I hope remember that's linked to drag. And we are generally dealing with slender body shape. For referencing, some examples are showing in our first lecture. Therefore, a special approximate form of the Euler equation, which applicable to hypersonic slender bodies, is useful in studying the aerodynamic properties of such bodies. And the purpose of this our module is to obtain these equations called the hypersonic small disturbance equation. So we will follow an approach frequently employed in aerodynamic theory. Instead of using the flow velocity itself as a dependent variable, we will deal with the change in velocity relative to the free stream, namely the perturbation velocity. For example, consider the two-dimensional flow over the slender body, which shown in this slide. At any given point in the flow field, the vector velocity is v. This is resolved into x and y components, u and v in our case, respectively. Okay? In turn, u and v can be expressed in terms of changes in velocity relative to the x and y component of the free stream velocity, right? And these changes are denoted by u stretch and v stretch, respectively, and are defined by these two expressions on the top. Maybe some is problem. I just to remember you here as my picture is closed. It will be u equal v infinitely plus u stretch, and v equal v stretch simply. The preceding relations are written for the case where v infinity is aligned with the x-axis, as we can see in this figure. And hence, the y component of v infinity is simply 0, right? The changes in velocity u stretch and v stretch are called perturbation velocity. You know, in general, they do not have to be small. And in this module, we are considering the hypersonic flow over a slender body. In such a case, U stretch and V stretch are assumed to be small relative to the V infinity, but not necessarily small relative to the free stream speed of sound. And hence, we will assume that we are dealing with small perturbation. Small perturbation, we may describe this very simple expression. U stretch many times less than V, and V stretch the same many times less than V infinity. To study the nature of this perturbation further, consider the velocity at a point on the surface of the body, as shown in this slide. Here we have this point. The body surface is given by expression y proportionals f from x. And hence, the flow tangency conditions dictate that we have expression at this form. V stretch over V infinity plus U stretch. It's simply as a relation between dy over dx. But however, examining our figure from this, we see that dy over dx we may reproduce as the relations order of d to L. So this symbol means order of. So let us define as d over L, it's a tau, or our slenderness ratio. Okay? So from our previous equation, we might found that V stretch over V infinity plus U stretch, it will be dy over dx, or order of from tau. Okay? Now, why? Because we have U stretch many times less than V infinity. So we may rule V stretch over V infinity as order of from tau. And let A infinity is a free stream speed of sound. From this last equation, we may write that V stretch over A infinity will be expression as V infinity to A infinity as order of from tau. Or rewrite in more simple expression the same. Okay? So we may rewrite this as a slenderness ratio. Tau. Slenderness ratio is a relation d over L. And clearly, well, from our last equation, here, this last equation, the strength of the disturbance in the flow, I mean, relative to A infinity here, is of the order of the parameter, is the order of parameter M infinity times tau. And this parameter will be identified as the hypersonic similarity parameter in the next our model. Okay? Okay. So, however, for the time being, simply keep in mind the definition of the slenderness ratio, tau proportional to d over L, and the fact that the product M infinity times tau is an indication of the strength of the disturbance created by the body in the flow, as expressed by the V stretch over A infinity. Now, let us express the steady Euler equation in terms of the perturbation velocity U stretch and V stretch. That is our equation. with zero time derivatives for steady flow, where we replace u with v infinity plus u stretch and v with v stretch, and certainly as w with w stretch. And we can obtain these equations, as you can see on the right side of our slide. So note in all these equations that only the velocity are expressed in terms of perturbation relative to the fresh stream volume. The remaining flow quantities P and rho, as you can see here in this equation, are still carried as their whole value. Now, sometimes a perturbation analysis will also deal with changes in all the dependent variables relative to the free stream. In other words, a perturbation pressure P stretch and perturbation density rho stretch would be defined as P equals P infinity plus P stretch, and rho the same, rho infinity plus rho stretch respectively. That's very simple, okay? Oh, but this is not necessary in our present analysis. All these equations, in all these equations, P and rho are usual whole value of pressure and density. And we wish to non-dimensionalize all these our equations. And moreover, we wish to have non-dimensional variables with an order of magnitude of unity for reasons to be made clear later. Okay? So, to obtain a hint about reasonable non-dimensionalizing quantity, consider the oblique shock relation in the limit as m infinity became to really as infinity, very, very large value obtained from our lecture number 2. You may refer it if you're interested. So also note that for a slender body at hypersonic speed, both the shock wave angle beta and the deflection angle theta are small. Okay? So, hence, we can rewrite the sine beta, it will be as simply the sine theta, or simply equal the theta, or we may be as simplified to dy to dx, and finally can simplify it as tau. And thus, these are equations repeated here for more convenience. P2 over P infinity get us 2 gamma divided by gamma plus 1, and all of this times m infinity square times sine square from beta. In this case, we have the order of magnitude relation in these expressions. P2 over P infinity get us this expression from m infinity square down square. Are you agree? So what it means? It means as order of expression. Order of expression here. P2 to P infinity, we may rewrite as order of m infinity square times tau square. And this, in turn, implies that the pressure throughout the shock layer over the body will be on the order of our m infinity square times tau square, and next step times P infinity. Hence, a reasonable definition for a non-dimensional pressure, which would be on the order of magnitude of unity, it will be, in this case, P uh, average. It's a P over gamma times m infinity square times tau infinity square and P infinity. The result for the gamma will become clear a bit later. Okay? So, but now, in regard to the density, consider our equations will be repeated in this form. So the density ρ2 over ρ infinity get us gamma plus 1 in nomination and gamma minus 1 in denomination. Suppose for gamma equal 1.4, it's normal thermal condition, and ρ2 over ρ infinity became a 6, which for our purposes is on the order of magnitude near unity. And hence, a reasonable non-dimensional density is simply will be ρ average as non-dimensional ρ over ρ infinity. In regard to velocities, we just consider our expression repeated in this form. u2 over v infinity get us 1 minus, in nomination, 2 sine squared beta, in denominator, gamma plus 1. Now, define the change in the x component of velocity across the oblique stalk as du is difference between v infinity and u2. And in this case, we will have next expression, delta u to v infinity. It's exactly as v infinity minus u in nominator divided by u v infinity. And that gives us as 2 sine squared beta over gamma plus 1, or order rho from tau. Okay? And this implies that the non-dimensional perturbation velocity u average stretch, which is also a change in velocity in the x direction, okay, and should be defined as u average stretch as u stretch over v infinity times tau squared, in order to be of an order of magnitude of unity. Are you agree with me? Now, and finally, consider our next equation repeated here in this form. v2 over v infinity get us expression as sine to beta divided by gamma plus 1. And expression delta v to v infinity, which will be, look, as v2 to v infinity, and will get us, look for this one, sine 2 beta over gamma plus 1, or we may write as order of from tau, okay? And this implies that the non-dimensional perturbation velocity v average stretch out to be v stretch over v infinity times tau, which is on the order of magnitude of 1. Because we are dealing with slender body, tau is a small number and much less than unity. And hence, by comparing our equations, we see that delta u, which varies as a tau square, is much smaller than delta v, which varies from the tau. Therefore, we can conclude, in the case of hypersonic flow over a slender body, that the change in v dominates the flow. That is, the changes in u and v are both small compared to the v infinity. but that the change in V is large compared to the change in U. And this fact was observed earlier in our previous section. Okay? And in conjunction with an argument that the major changes in properties in a hypersonic shock layer of a slender body takes place across the flow rather than along the flow. Okay? Across the flow rather than the long. And next, based on the preceding argument, we define the following non-dimensional quantities, all of which are on the order of magnitude of unity. Note that we add a third dimension in the z direction, and that y and z in the thin shock layer are much smaller than x. So we can write this expression on the top, on the left side of our slide. We should note it here. The Pareto quantities here are different than the Pareto quantities used in previous expression. But because the present module is self-contained, there should be no confusion. In terms of the non-dimensional quantities just defined, our expression can be written as next in the bottom of this slide in left side. Noting that rho infinitive times v infinitive square will be represented as gamma p infinitive over gamma p infinitive, yes, bound to run, writing, times rho infinitive v infinitive get us gamma p infinitive v infinitive over a infinitive, or get us gamma p infinitive m infinitive square. And we have next expression here, rho average, in parentheses 1 plus u average stretch tau squared times du stretch average to dx average, and this all will be get us negative dimension. What it means negative dimension? In opposite direction, okay? And we can rewrite expression this one, or we may transcribe in this most simple expression. Look, this will be all equivalent one with other. Generally, they repeat the main part. What's the difference? This identical du stretch, dv stretch over dx, rho v stretch as the same. We have, instead of du stretch, we have dv stretch average divide. The same identical, and this component a bit different, right? dv, and get us the same negative dp stretch over dy instead of over dx. Okay? The same identical we can choose as this last equation. All the coefficients before absolutely identical, except the variation into the nominative in both sides. Okay? So from this equation, we can rewrite our expression in a bit more longer form on this part of the slide. For more compact form, we can rewrite as you can see here. Examining all these previous equations, but close. Okay? And let's see, because of our choice of non-dimensionalized variable, each term in these equations is of order of magnitude unity, except for those multiplied by tau squared, which is very small. And therefore, the term involving tau squared can be ignored in comparison to the remaining terms in all our equations. And we can rewrite our equations as you can see in the right side of our slide. Okay? All these equations are the hypersonic small disturbance equations. They closely approximate the hypersonic flow of a slender body. They are limited to flow over slender body because we have neglected terms in order to the tau square. And they are also limited to hypersonic flow because some of the non-dimensionalized terms are of order of magnitude unity only for high Mach numbers. And we made certain of this in the argument that preceded the definition of the non-dimensional quantity. And hence, the fact that each term in all our equations is of the order of magnitude unit, which, generally speaking, is essential for dropping the tau square term in all our equations, and hold only for hypersonic flow. So our equation here exhibited at interesting property. Look for U average stretch in this equation. You can find it only in the next equation. And therefore, in the hypersonic small disturbance equation, U's average stretch is decoupled from the system. In principle, this first equation and next four constitute four equations for the four unknowns. Which unknowns we have? We have rho stretch, P stretch, and V stretch. Average. Rho, P, and V. Right? And forgot, and W. After this system is solved, then the U average stretch follows directly from our second equation. And this decoupling of U stretch average from the rest of the system. And it will be another ramification of the fact already mentioned several times, namely that the change in velocity in the flow direction over a hypersonic slender body. In this case, we have a much smaller than the change in velocity perpendicular to the flow direction. So our four equations were obtained from the general nonlinear governing equation of motion. But in spite of containing the assumption of a small perturbation, and all these equations are still nonlinear. And this is one of those distinctions that sets inviscid hypersonic flow apart from subsonic and supersonic flow. The small disturbance equations for subsonic and supersonic flow are linear and lead to some straightforward solutions for subsonic and even supersonic flow of a slender body at small angles of attack. Not so for hypersonic flow. The hypersonic small disturbance equations are a set of coupled, nonlinear partial differential equations for which no general analytical solution has yet been obtained for today. And this circumstance is simply another ramification of the fact that there is nothing that is linear in hypersonic flow theory. Or simply, hypersonic flow is inherently nonlinear. The hypersonic small disturbance equations, however, are used to obtain some practical information about hypersonic flow of a slender body. The first such use will be made in the next module dealing with hypersonic similarity. So let's come to the next part of our lecture, hypersonic similarity. The concept of flow similarity is well entrenched in fluid mechanics. In general, two or more different flows are defined to be dynamically similar when, first of all, the streamline shapes of the flow are geometrically similar. And second, the variation of the non-dimensional flow field property is the same for the different flows when plotted in a non-dimensional geometric space. Such dynamic similarity is ensured when the body shapes are geometrically similar and certain non-dimensional parameters involving free stream properties and length, called similarity parameters, are the same between the different flows. In the present module, we discuss a special aspect of flow similarity that applies to hypersonic flow of a slender body. In the process, we will identify what is meant by hypersonic similarity and will define a useful quantity called the hypersonic similarity parameter. Let us consider a slender body at hypersonic speed. The governing equations will be next four equations here. On the left side, to use equation must be added the boundary condition at the body surface and behind the shock wave, right? At the body surface, the flow tendency condition is given by these next equation at sum must be equal to 0. In terms of the perturbation velocity, we will define as expression for V and M and units. So our equation gets us the direction cosine and x and y and z are in the xyz space, logically simple. And these values are somewhat changed in the transform space as nx average and y average and z average. That value denotes the direction cosine in the transformed space. And we have within our slender body expression as a time tau in the first for n. And the rest of all will be remain. The mathematical derivation of these three equations is left as some homework problem. It's for that person who is interested. But however, the results are almost intuitively justified. For a slender body aligned along the x-axis, the unit normal vector at the surface is almost perpendicular to the surface. And this means that our nx is a small number, much less than unity, whereas ny and nz can be close to unity. In the transformed space, the slope of the body is increased by factor 1 over t tau tau. And the unit normal vector in the transformed space is now more tilted with respect to the x-axis by the same factor 1 over tau, 1 over tau. And hence, the direction cosine with respect to the x-axis is now will be an average x as nx over tau. At the same time, we can say that n average y is nearly the same values as the n y. And the same situation with n average z will be as approximately the same as simply mz. And this is the justification for our equation. With the relations given in our equations here, the boundary condition becomes in the next form here. These two boundary conditions, okay? Consistent with the derivation of the hypersonic multi-Starbuck equation, we neglect the terms of order tau square, and yielding the final result for the surface boundary condition, as you can see on the right side of this slide on the top, n average x plus v stretch average and y edge get us all as a sum of zero. So the shock boundary condition consistent with the transformed coordinate system can be obtained as follows. Consider we have repeated this expression for the rho 2 over rho infinity, or rho 2 average, and get us expression in this form. So, for hypersonic flow over a slender body, we have a b beta is a small. In this case, we may rewrite the sign beta as a small value, may be approximately equal as a simply beta. In this case, we may rewrite as dy over dx for our body as exactly as this for average y and x times tau. Okay? Here we have the dy over dx average is the slope of the shock wave in the transform space. And thus, we may rewrite our equation for the average 2 as this non-compact equation. Repeating this for the pressure, we can rewrite P2 over P infinity as this expression, and recalling that P average as a P over gamma times m infinity square times tau square times P infinity get us become as this expression non-compact, but it's exactly as we can see. Okay, P2 and B there repeatedly. And we can the same identically rewrite for the PT average. And PT average may be rewrite in this form. And more compact this form. After transformation, we can set these bottom equations here. 2 over gamma plus 1, an expression from dy the average to the x-axis for slender body square, plus 1 minus gamma in nomination. In denomination, 2 gamma m infinity square times square, tau square. Repeating this equation, we can write expression for u2 over 2 infinity. 1 minus 2 m infinity square in parentheses times sine square beta minus 1. In denominator, we have simple gamma plus 1 parentheses times m infinity square. And recalling that u2 is this expression and u2 stretch average as this one, we can become the next two expressions, 1 and 2. And finally, we can go at this expression of the bottom. Identically, repeating for the next expression, we can go our expression at this 2 for the rho 2. P2 over P infinity get us this expression, where we have P average as a P over gamma times M infinity square tau square times P infinity. Look at something like already you saw. After transformation this and this, we can found expression from V average stretch. And that's all equations on last two slides represent boundary conditions immediately behind the shock wave in terms of the transform variable. But we should know that these equations we obtain from the exact oblique shock relation, making only the one assumption of small wave n. Nothing was said about the very high Mach number, and hence all our equations should be applied to moderate as well as large hypersonic Mach number. Examine carefully the complete system of equations for hypersonic flow of a slender body. The governing flow equation on last two slides, the surface boundary condition and the shock boundary condition. For this complete system, the free stream Mach number m infinity and the body slenderness ratio tau appear only as a product m infinity times tau. And this appears only in the shock boundary condition. As we have stated, the product m infinity times tau is identified as the hypersonic similarity parameter, which we could denote by K. We denote it here on the top on the left. Hypersonic similarity parameter K, the meaning of that parameter becomes clear from the meaning of the hypersonic similarity parameter becomes clear from an examination of the complete system of equation. Because expression m infinity tau and gamma are only parameters that appear in these non-dimensional equations. And then solution for two different flows over and two different paths affinely related bodies, I mean bodies that have essentially the same mathematical shape, but that differ by a scale factor on the one direction, such as different values of thickness, and that will be the same in terms of non-dimensional variables like U average stretch, V average stretch, etc. In case if gamma and m infinity tau are the same between the two flows. And this is a principle of hypersonic similarity. For a finely related body at a small angle of attack alpha, the principle of hypersonic similarity holds as long as in additional to gamma and m on infinity tau, alpha over t tau is also the same. And for this case, the only modification to the preceding derivation of Q in the surface boundary condition, which in our case is slightly changed. So for a small alpha, we can write as expression, rewrite as expression in this form, and that should be equal to 0. The derivation of this equation, as well as analysis of the complete system equation, for the case of a small alpha, is left to the very simple expression. So, in summary, including the effect of angle of attack, the solution of the governing equation along with the boundary conditions takes the functional form as a p for the p depending from x, y, z average, gamma n infinity tau, and alpha over tau Okay? And the same expression for the raw average. Yeah, it depends the same, etc. Therefore, hypersonic similarity means that if gamma, m infinity tau, and alpha over tau are the same for two or more different flows over affinely related bodies, and then the variation of the non-dimensional dependent variable over the non-dimensional space will be rewritten as this expression. Okay? And this is clearly the same between the different flows. Now, consider the pressure coefficient can be defined as our expression here. Cp will be P minus P infinity and half rho or infinity times V squared infinity and get us this expression. And this can be written in terms of P average as this form. Because P average is dependent from x, y, z average, gamma and infinity tau, and our alpha over tau, then our last expression for Cp here becomes the following functional relation as model. Cp over tau phi will be first function from the x, y, z average, gamma and infinity tau, and alpha over tau. From this bottom equation, we see another aspect of hypersonic similarity, namely that flow over affinely related bodies with the same values of gamma, m infinity tau, and alpha over tau will have the same value of Cp over tau squared. The viability of hypersonic similarity is reinforced by results that we have already obtained in lecture number 2. So, from that lecture, the hypersonic shock relation for large m infinity and small deflection angle will be obtained in turn as a m infinity, but it turns as a theta and get us as a k. So we can say as the hypersonic similarity parameter. And this is precisely the same as m infinity tau, because for slender body, theta is approximately as theta tangent theta, and get us approximately as d over L for the same tau. So in this case, its functional form, we can repeat it in the next form. Cp over t tau squared is approximately equal Cp over theta squared as a function from k and gamma. Hope you remember our case, k as a hypersonic similarity parameter. So this states that Cp over tau squared for the flow behind an oblique shock, and hence over a wedge over slender ratio tau, is a function of gamma and k, function of gamma and k only, right? So our previous equation obtained from the hypersonic expansion wave give analogous result. And hence, the results in previous lectures are precise to the concept of hypersonic similarity discussed in previous module. So, hypersonic similarity carries over to lift and wave drag coefficients as well. Now let us examine this in more detail. To begin with, assume a two-dimensional body of length L, and hence a plan form or top view area per unit span will be as the length as the one unit. Dividing this equation by tau u, and combining expression, we obtain the following relation in this case as integral from 1 to 1, 0 to 1 unit, and get us function c from gamma m infinity tau and alpha over tau. So, summarizing the preceding result, we can get this expression on the right bottom part. F2 AF3 is a function from gamma m infinity tau and alpha over tau. Right? So CL over tau and CD over tau will be a reference to plan form area. Right? Sounds nice. Let us repeat the preceding arguments, except now for a three-dimensional body. The considerations are only slightly more involved as follows. Now, consider we have an arbitrary body which shows in XYZ coordinate x, theta. In an illicit flow, the net aerodynamic force is caused by the integration of the surface pressure distribution over the body. Okay? So, consider an elemental force as P ds caused by the pressure acting on the element surface area ds, as shown in this. So, the component of this force in the z direction will be in this for z direction, yeah, look in the vertical, will be, how we can draw, will be as a p dx to dy, okay, where dx to dy is the projection of ds here into the xy plane horizontal, and hence the leaf will be expressed as look like here integral from our f pxyz from this times dx to dy. In terms of the transformed variable, our first equation becomes in a more complex form. Here we define the lift coefficient for the three-dimensional body as CL. This is lift over Q times S, and Q, this is gamma over 2 times pressure infinitive and times m squared infinitive. And the area S here is taken to be the base area in contrast to the platform area used for our preceding two-dimensional case. Letting By and Bz be the half width and half height of the base respectively, then we maybe say that S will be proportional By to Bz and proportional to By to Bz average from the tau. But we should notice that S is proportional to tau squared, and hence we may rewrite our expression for the still proportional from these big expressions. Now, recall that P stretch from X, Y, Z average is obtained from the solution of the hypersonic small disturbance equation for our given gamma, m infinity tau, and alpha over tau. Therefore, the surface integral given in this equation will depend only from the gamma, m infinity tau, and alpha over tau. With this in mind, yes, a previous equation and the upper equation, this leads to functional relations as a CDL over tau in this our form. Now, let's return back to the component of the P times dl, right? Right? In the x direction, and P dy to dz And hence the drag D can be right in this form. Look, this form as drag as the colleague. Do you have big difference? Dx over dy here, and here we drag in which direction we have. Yeah, as the drag, we have dy to dz. So drag may be rearranged in the more biggest form here. And coefficient CD will be rewrite in that form. Or simply we may write as CD over tau squared as a function like from CL, from gamma, m infinity tau, and function from alpha over tau. So reference to base area. Okay? Examine the result summarized in the preceding two boxes, namely the result for CL and CD for a two-dimensional flow, coefficient CL and CD for a three-dimensional flow. And from this result, the principle of hypersonic similarity states that affinely related bodies with the same values of gamma, m infinity tau, and alpha over tau will have one. The same values for the CL over tau square and CD over tau u for the two-dimensional flow when reference to the plane form area. And the same values for CL over tau and CD over tau squared, CL over tau, CD over tau squared, for the three-dimensional flow when reference to the base area. Okay? The validity of the hypersonic similarity principle is verified by the result as shown in this slide, obtained from the experimental works of Knight and Eric. Consider first as the left diagram, which shows the variation of the Cp over tau squared as a function of distance downstream of the nose of a slender ogive cylinder. We mean this here as a function as a x is x over L, expressed in percent of nose length. Two sets of data are presented, and each for a different m in infinitive, 3 and 6 in our case, and tau. And we have two different tau. But such that the product as a k equal m infinity tau is the same value, and namely here we have 4.5. The data are exact calculations made by the method of characteristics. So the data, the hypersonic similarity say that the two sets of data should be identical, which is clearly the case shown in this experimental graph. And we can see from 3 marked as a row as a 6 and all the same identical. A similar comparison is made in right figure, except for a higher value for the hypersonic similarity parameter, and namely k in our case, keta 2. The conclusion is the same. The data for two different values of m infinity for 6 and 12 and tau, but with the same k factors are identical. An interesting slight side is also shown in this figure. Two different methods of characteristics calculations are made. One is some assuming irrotational flow, means, and in reality, the flow over the ogive cylinder is rotation because of the slightly curved shock wave over the nose. And the effect of rotationality is to increase the value of Cp. As you can see here in humans, a percent of nose length and value as Cp growing. However, researchers Nice and Eric state that no significant differences between the rotational and irrotational calculations resulting for the low value, as you can see for K 0.5 and K for 2, which is why only one curve is shown on the left side. Okay? One can conclude from this comparison the almost intuitive fact that the effects of rotationality became more important as M infinity and tau, or both are progressively increased. However, the main reason for bringing up the matter of rotationality is to ask the question, would we expect hypersonic similarity to call for rotational flow? The question is rhetorical, because the answer is obvious. Examining the governing flow equation upon which hypersonic similarity is based, namely, we know that they contain no assumption of irrotational flow because they apply to both cases. And hence, the principle of hypersonic similarity calls for both irrotational and rotational flow. And this is clearly demonstrated in our right figure here, where the data calculated for irrotational flow for two different values of m and tau, but for the same k, fall on the same curve, and the data calculated for rotational flow for the two different values of m infinity, 6 and 12, and tau, 0.3, 0.16, but for the same k. So figures left and figures right contain results at zero angle of attack. For the case of bodies at angle of attack, our similarity analysis has indicated that alpha over tau is an additional similarity parameter. And this, as well as the general principle of hypersonic similarity, is experimentally verified by the wind tunnel data, as you can see from this diagram on the left side. Experiments reported some pressure distribution over two sharp right circular cones at various angles of attack contained in the NACA AIM 10 and 14 inches supersonic wind tunnel. The free-stream Mach number were 4.46, yes, 4.46, and 2.75. And the cones had different slenderness ratios, such as K equal 0.91, 0.91, okay, 0.91 for both cases. Because the flow was conical, the values of Cp on the surface, yeah, were constant along a given ray from the node. But because of the angle of attack, Cp varied from one ray to another around the cone as a function of angular location. Okay? So notice that the data along any given ray for the two different values of m and tau, but both such for k equal, in our case, 0.91, fall on the same curve when plotted versus alpha over tau. And hence the data on this figure are a direct experimental verification, you can see the experimental dots, of hypersonic similarity for bodies at tangle over time. But note that at alpha equals 0, all of the cards passes through the values of CP, predicted from the exact Coulomb theory. So, hypersonic similarity appears to hold even at very moderate hypersonic Mach number. And if we're replacing M infinity tau with a tau times square root from M minus 1, this closely approximated for the single similarity rule will be held for the entire Mach number regime, starting yet about the transonic range and going to an infinite Mach number. I think it's enough for today. Next lecture will be hypersonic small disturbance theory. Okay? I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.